I'll hand it off to Andrew.
Right. Thank you and welcome everyone. So I'm Andrew Miller, founder of a company called Qcelerate. There's the logo on the left. So initially when I started the company, I wanted the company to focus on quantum computing, hence the name Q and accelerate, kind of like accelerate. But because the market shifted, I'm now doing AI ML consulting. So that's the main thing. And I'm based out of Holly Springs, North Carolina, kind of close to Red Hat headquarters, if you're familiar with Red Hat. And so today I wanted to talk about disease detection, specifically as it relates to quantum computing. And so let me get started. And the first thing that I want to talk about is kind of the benefits, the real world benefits of doing disease detection. And specifically what it offers is if you detect a disease early, you have a huge saving, and also you might be saving lives, right? You know that a lot of cancers, if you find it early, you can cure it completely, or you can reduce the cost of care, or you could prolong life. And so there's a lot of benefits, economical and just to human life and our civilization. And so that's one of the biggest benefits is detecting disease early. The other big one is personalized medicine. So if we can tailor care to an individual, to their disease history or health history, we can then improve the care. And a lot of times, like at least in my personal health, like I struggle with the hospital just kind of following a generic protocol, and they're saying, well, that's what everyone gets, and you have to get the same thing. And so I think we can get a lot more people a happier and also healthier if we personalize our medicine. And so that's another big benefit. If and so for disease detection specifically, because it works at two levels: individual and then and then population. The other big benefit is drug discovery. And specifically here, I talk about simulating molecular interactions. And I hope you can see, by the way, like you can read somewhat. But in essence, and it's kind of like you think about it, how do you tie disease detection to molecular interactions? Like, well, how do you connect the dots, right? And so the reality is when you are sick, you go to a doctor, they do a blood testing. And going back to the concept of personalized medicine, well, one thing you can do is get the biological samples and analyze them for different called metabolites, or you could do genetic analysis too. But in essence, you'll get some molecular composition of your blood or whatever other sample that you're using, and then you can sort of build a history of the disease progression. And that history, you can build a digital twin of yourself, and then you can test how a specific novel, non-existent drug can metabolize in your system, so you will know with more degree of accuracy and confidence that this specific proposed drug or treatment that might be even personalized to you is going to actually work with certain degree of confidence. The other big part of the benefit is population health. So I talked about the individual, but when COVID happened, everyone was unprepared. None of us knew, but the reality of it is if we could detect early signs earlier, we could be more prepared, and so then we wouldn't have a disaster such as we had before in many times. So that's another big benefit. All right, so the big thing with quantum computing, everyone is talking about quantum advantage. So, and everyone is promising, next 10 years we're going to get quantum advantage. It's going to be great. It's going to solve all the world's problems, which is not true. But but then let's imagine that we do get there. We have quantum advantage. Where does it come from? And so one of the biggest things where it comes from is from the fact that qubits can represent a lot more states simultaneously. And so then here on screen, I have a Bell sphere. And in essence, you have on the top ket 0, which is the basis state. And then on the bottom, you have ket 1, which is another state. And so then your qubits exist in superposition of those two states. And the idea, so in the case of only one qubit, you'll see that you only have basically two states possible. But as you add more qubits here on the bottom left, you will see that you start basically adding a lot more potential states that you can model and represent simultaneously, meaning that the information is being processed at the same time, and it's not the same as if you were using like multiple cores or a similar technique with classical computers. All right, and I'll get to explain why that is not the same. So the other advantage that you will have is so, and this is really why it's not the same to a classical computer. Classical computer, you have to synchronize, different cores or threads. But here, the idea is that that synchronization sort of happens. How do I say it? Physically. So there's not necessarily an effort on your part to do this. So long as you encode the information and guide it towards the right solution, you will kind of get that out of the box. And so in this example, I'm basically showing how you would potentially, in reality, this not how you would really do it, but like just pure, theoretical example, you have four different indicators for a disease, like such as blood glucose, blood pressure, blood cholesterol, and then BMI. And you can encode them using those base states that I mentioned, such as shown on the left, which is, for example, for glucose, you can say 0 is normal and 1 is elevated. And so the same way you could do for the other three. And then if you have 4 qubits, now you basically have a ton of states. I can't do math in my head, I'm sorry. 2 to the power of 4. So you have that many states, and what you can do is sort of model the interactions. So here on the bottom, I'm showing you how, what specific states would mean. Like in the case of bottom right, it's high glucose, high blood pressure, and that can basically mean that the person is having a diabetes, plus they might have a hypertension comorbidity. So that's sort of the example where you're at the same time you're tracking different interactions between the variables. All right. So the next advantage for quantum systems is optimization. So if we're using like a classical algorithm, a lot of times the problem you'll especially in optimization, the problem you'll have is you get stuck in a valley and the algorithm can't get out, right. You get stuck on a local minima and you need to actually go somewhere else to find it. So there's techniques to kind of get around that. But the quantum systems don't have that problem because of the quantum tunneling effect, where you can overcome basically a potential because it's a wave. And so unlike the classical algorithms where you have to kind of come up with tricks to get around that. And so you can escape the local minima and then find that global minima if it exists. The other source of a quantum advantage is pattern recognition. And when I read this, I was like, quantum interference can enhance signal. How can interference help me enhance signal? But that's actually kind of the main technique I think that a lot of quantum computing these days is implemented, which is you use constructive and destructive interference. So on the top left, you'll see that what we're doing, we have two waves and we combine them in a way that produces one stronger wave. So here we basically amplified signal. And then in the other case, we have two waves that cancel each other out, so there is no signal at all. And so a lot of, like, if you look at D-wave machines, which is quantum annealers, that's the whole principle, right? You're basically figuring out how to create that constructive interference when you need it, and destructive interference when you, let's say you're doing binary classification, right? You will say that the disease is there, give the strong signal, disease is not there, give weak signal. So that's the idea. And it comes from, if you look at like, physics double slit experiment, right? Or any type of really waves, right? And you create that, two waves interfering, you can get sort of patches where the wave, there's no wave, right? And there's patches where a wave is strong. So it kind of comes from that principle. All right. So for healthcare specifically, I talked about like overall, right? How is this helpful and how is quantum computing advantageous? But now let's talk about sort of the meat of this presentation, which is in context of healthcare, how would you use a quantum computer to identify disease and identify it potentially early? And so the meat of the presentation is sort of a toy example of a toy problem. It really just demonstrates how you can take a quantum system and map a problem onto it, but it's by no means it's the best way to do it. And in fact, like there's a lot of art that goes into it, like specific looking at the history. Here, it's very sort of snapshotty. You're only looking at like the current state, but most clever algorithms and models will analyze prior history and all kinds of other techniques to get to the sort of the better performance of the model. So the first thing I want to talk about is, I mentioned high dimensionality, right? So you have many different states. So, but how would you map a patient data into qubits? So this kind of shows it, an example of it, which is you have, four patients, and they have different diseases that they had previously in the past, and we're basically one-hot encoding. So if the person had or has hypertension, we'll just say 1, and if they didn't, we would say 0. And so you'll see that, and we do that for a number of indications or conditions. Now, you can, like, typically you will have a huge table or matrix of these, right? So, like, because it's not just 5 that are going to determine a specific outcome. Doctors try to kind of distill it. They sometimes come up with a way to say, for this specific disease, we know only like there's 5 major determinants, and so they will kind of limit it. But that's where the art part comes in. All right. The other big part of this is also using superposition, and this is how it's different from classical computers, where the infamous Schrodinger's cat. But in our case, it's not necessarily a cat, right? It could be that superposition state of, for example, a person having some sort of a heart condition. So they're kind of quote unquote having it and not having it, but the reality of it is you can steer the system to give you the right answer when they're more likely to have it, and the wrong answer when they're less likely. So it's not 50-50 that the cat is dead and alive at the end. It's you can drive it towards where it will tell you, yes, this is highly likely to be the case of person having a specific, for example, heart condition. And that's sort of the way to leverage superposition. And the other part of where healthcare connects with quantum computing, so if you're familiar with like machine learning, you'll have, like, for example, neural networks, right? You'll have weights that you're learning as part of your process. So for this demonstration, it's very similar, but instead of weights, so in this visualization on the bottom right, you'll see that u of theta, and the idea is that theta is just some angle, but the reality of it is acts kind of like a weight. That's the way that I like to describe it. And this is a more in-depth representation of that. So this is at a high level. Just look at it as a block box that you're learning some sort of weight, and then the weight is just encoded in the quantum system somehow. Now, how would you go about doing this? So I talked about sort of having that table of one-hot encoding, or whatever other data that you have. It needs to be converted to a state that a qubit can represent. And so this is a more in-depth visualization of that process. So you'll get the raw data from whatever data set you're using. You will then pre-process it, and we'll get to more details of how you do that. And then you'll use what's called a feature map that, in essence, converts the classical information into qubits. And then you can start doing that sort of learning step where you're learning theta. And I'm oversimplifying by saying theta, but in essence, if you dumb it down to like one dimension, you could think of it that way. And then you're basically, so that table that I showed you with multiple patients, you're running each patient, one at a time. And so this is not truly a purely quantum algorithm. This is a hybrid algorithm where you're basically a classical computer is controlling quantum system to learn and optimize for the most optimal theta to solve your specific problem. In our case, it's disease detection, basically classifying, does the person have the disease or are they likely to have the disease. So for this demonstration, I used Mimic 4 dataset. Anyone can get it. So it's based on ICU patients, I believe in the states of Massachusetts. The data is de-identified, but you need to pass the test in order to get access to it. And it has things like demographic data, lab values, vital signals, ICD codes, and it's also temporal data, so you will know when certain events occurred. Now, because it's ICU data, it's biased, and also because it's Massachusetts data, it's biased. So probably any scientific publication based on that isn't going to be, if you're trying to apply it to the nation in general, probably not going to be great. But a disclaimer here, basically. So the other part of the equation is, for this demonstration, I'm using IBM Quantum, which is a system where you can access real hardware that is hosted by IBM through their IBM Quantum Cloud. And I'm using a package called Qiskit, which is a Python library that allows you to instruct a quantum system to perform certain actions. And the final piece of it is advanced analytics, where you, in essence, do some feature engineering. So it's not just a simple, pass through. You're actually doing something a little clever, not extremely complex. So note about current limitations. Here for this demo, I'm basically using 4 qubits. So you can't map 100 features that easily into 4 qubits. So there's going to be obviously loss of data or loss of accuracy due to this. For data set scale, so it's a demonstration, so it's not like a full-blown. I'm running this on like a sample of 500 patients. So the training time, obviously, if you want to run larger sets, is going to increase. And we're still in the age of noisy quantum computers, so it's not going to be great, just to set the expectation. So I talked about advanced analytics. This is where sort of I need to explain what I meant by that. So we start with just loading the data from Mimic data source. And then for this specific example, I'm basically training a model that is going to detect sepsis. And is going to basically say, yes, this person is likely to have sepsis. And so the doctors know that there are certain biomarkers for sepsis. So here I have a list of biomarkers that might be indicative of sepsis. And then on the bottom left, this sort of a snapshot is just part of that big table containing the different indications. But what I do is take the mean, the min max standard deviation and the mean of each of the labs, and basically jam that all into a table. The next step is I'm looking for patients that have sepsis because I need to have labeled data, right? How am I going to train a classifier? So I'm grabbing some of those patients, and in essence, I'm doing some sampling to get a more representative. I'm not going over the sampling, but the code is on GitHub, so there'll be a link I'll publish. I don't know if the repo is already open to public, but I'll make sure to open it, and I'll upload the slides on DevConf's website after the talk. But the idea is that I talked about sort of only having 4 qubits, right? That's not a lot. You can get access to 100 qubit systems and more, but you still, if you're doing something clever and or something that's more real world, you probably want to have more features than 4 features, right? So here I kind of demonstrate how you might be able to do that, doing what's called principal component analysis. And the idea is basically it's a compression technique, like used, for example, for image compression here. I don't know if it's very easy to identify, but there's 3 levels of PCA compression here with the image, and there's some loss of quality, but overall you can still make out the features. And so the idea is that we take sort of, let's say we have 100 different features, like let's say, conditions in that one hot encoding, or labs, different kinds of labs, I can condense them. Even though I have 4 qubits, I might be able to condense like 16 of those features into 4 qubits by doing PCA. Yes, there will be some loss of data, but at least like, I'll get sort of the majority of the features somehow crammed into that the 4 qubits. So here in this example, I'm basically jamming 140 of them into 4 qubits. And the last step, we talked about sort of the Bell sphere, right? And so you can't just have like an arbitrary value, so you have to normalize the data before you feed it into the system to be minus pi range. All right. So the last part is the encoding, quantum encoding. So this talks about how you would encode those classical bits or classical data into a quantum system. For this specific example, I'm using ZZ feature map, and the circuit is displayed below. But the idea, so ZZ, what does that stand for? I didn't know before giving this talk. Basically stands for the product of Pauli Z gate, specifically tensor product, and I will try to break down the circuit real quick. So on the left, you have the original qubits in their 0 state, and then they go through quantum wires, which are not real wires. But if you think, the way that I like to think of it is, if you think about quantum systems, like an actual optical fiber where light travels, so then you can kind of imagine that it's a fiber line. That's the way that I think about it. But if we talk about IBM systems, like this isn't real hardware, right? Because on the superconducting qubit systems, like there's no light, right? So, and in fact, these are logical qubits. On real hardware, you have physical qubits. So like 4 logical qubits might map to like 10 physical qubits. So but it helps to think about this logically. So you feed the 0 state into the Hadamard gate, and that basically what it's doing is putting the qubit in a superposition state. So in essence, it's not like how would I describe? If I go back to the block sphere, right? It's not with up or down state. It's somewhere in between. I think it's a 90-degree rotation. I got to go back, but in essence, it's some sort of rotation on the block sphere. And so once you've done that, the next step you'll see is the P step, that P block, and that's another rotation. I think, let's see. Yep. So this one is rotation around z-axis, and it's very hard to see, but in essence, it's 2 times x of whatever qubit number it is. But in essence, it's a rotation, and the purpose of that rotation is to how do I describe this? I don't even understand it myself. But okay, no. The purpose of this rotation is really prepare the qubit to be entangled, and so then after that you have this CNOT gates. So you see the dot, and then the other bigger dot with the plus sign, and so these will actually entangle the individual qubits. Right. Okay. Going back to the previous state, the purpose of that is really encode the classical data, right? Because you're passing in x of 0, which remember has been normalized to minus pi to pi range. So then you're encoding that classical information into the qubit, and then you entangle the qubits, and you're doing pairwise entanglement of those qubits, and that's what kind of this cascade of this plus sign and then p in between. That's actually entangling them, which is doing another z-axis rotation, and the angle is too tiny to see here, but you can download the slides and see it. Suffice it to say, you're basically entangling the qubits pairwise. And after you've done all that, then your data is encoded in the qubit states. So and the other thing is that these operations also take care of, so the initial sort of array of P gates handles encoding individual variables, but then you have encoding of interactions between pairwise interactions of the variables. So that's really the purpose. So you're tracking both individual variables and their interactions, kind of like in an equation. You have 2xy, 2xz, and so on. All right. Let's see. So the next part, which is the actual circuit, so that u of theta, where you have the weights. So this is where we're using rotation around y-axis to encode this. But in essence, and then some C0 gates as well. So the purpose of this, like I said, is kind of model the weights, and I'm gonna dumb it down like that because I think I'm running close on time, so apologies. But one thing to note about this specific circuit is that so how do we know that when we're running the data through it, that the theta we're picking is right? So for that, we're using Kobila algorithm, if I'm reading it right, and I don't know if I am reading it right. But it is one of the algorithms. You can probably use another one, whatever suits your heart. All right, and the last part of it is we then measure. So once you run qubits through this two circuits in sequence, and the other thing, these circuits, there's two reps of each. So they're not like the example that I showed is just to illustrate the circuits, but then you combine them and do two reps of each. And finally, you do the measurement. And so then based on the measurement, you can adjust, am I going in the right direction or am I going in the wrong direction? And so that entangled state gets condensed into, when you measure, you have the wave function collapse, which is you get 0 or 1 at the end. So all those superposition entangled states, sort of in between, cut, dead, and alive at the same time, that's all gone, and you actually know what the answer is. All right, so technical deep dive. This is what the code looks like. Those two circuits that I showed you, you really only need to make like a couple API calls to create those circuits. And then for the actual algorithm that's doing the learning, we're using an algorithm called VQC. And that's basically, it's very simple to do this. And kind of one of the talking points about this presentation is that anyone can do quantum computing. You don't need to have a PhD or a physics degree or anything like that. And it's, I think, going to be the same way that people write code. Thank you. People write code these days. You can write code for GPU, and you might have no idea how GPUs are built, how circuits are built in them, but you're harnessing full potential of those. Of course, you may still need to know like the nuances when you're developing applications that run on GPUs, like AI applications, but you don't need to have advanced degrees in electronics to do that. And so it's the same idea here, very simplified. So just think of it as like block boxes that are doing things for you. All right, so I talked in the beginning about sort of real hardware, but when you develop real hardware, access is limited. You may need to wait in a queue. So a lot of times we use simulators to try out the algorithm, make sure everything is kind of looking all right based on what we are expecting. And so then we can run on a real hardware, but real hardware is limited. So this is where I will kind of switch to PyCharm, and let's see if I can run this. So this is the actual code. There's about 400 lines of code. All right, so this is going to run on real hardware. And I hope that those quantum machines in IBM data center are up. So it's like I described, this is loading the mimic data. Now it's basically, it only found 100 cases of sepsis. So if we're doing 500 samples, you can imagine the prevalence rate. Now I'm not doing like actual. So if you're doing like said like this for real, you would be making sure that your prevalence rate in the sample is matching the prevalence rate in the population you're targeting. I'm not doing anything like that because it's just a demonstration. So I end up extracting 14 categories that I believe are most indicative for sepsis, and then using PCA, jam all that into 4 variables, and then that gets fed into a quantum circuit with 4 qubits. And then we're doing the actual training. So this is where we're sending in, one patient at a time, trying to figure out that theta. And so that theta is not a single theta because, the rotations, each qubit is going to have its own gate. So the rotations, if I go back to that slide, where that was this slide, right? So basically, each of these red blocks has its own theta. So we're learning that. All right, and so we finished the run on real hardware, and we get sort of the typical, confusion matrix and the various. See if I can zoom in. Oh, I have it on the slide. So. And so we have the typical, confusion matrix and some other matrix like metrics such as like precision recall F1, and there's a gazillion of metrics that you might need to look at. But the point of this is really not to say that this is the perfect algorithm, because it's not. This is just a demonstration of how you could take a real problem and map it into a quantum system and do it today. Future enhancements are, applying more advanced modeling techniques, doing multi-class classifications. Also, I didn't talk anything about like error correction, but we know there's error in the system, so there's algorithms that will combine gates in a way to correct for errors. So that's another thing to potentially add. Look at more features. And also benchmark this against, a classical computer doing ML. So those are future enhancements. And thank you for kind of listening to this. I was going at a 100-mile-per-hour speed, but I hope something stayed there. And so the links are here. You can connect with me on LinkedIn or email me. And I also linked the Qiskit website, which is the IBM's product to write quantum software, and the Mimic link is there as well. So again, thank you, and if there are any questions, I'm still here for a few minutes.
Thank you so much, Andrew. If anyone has any questions, I can pass the mic. But yeah, thank you.
So I know nothing about quantum computing, first of all. So, but IBM has, as part of the AI Alliance, a drug discovery working group, and they also have all this quantum equipment. And the AI Alliance is like a nationwide group of vendors and researchers who are trying to work on interesting problems. And one of them is drug discovery. So you should really be in that group.
All right. Sure. I'll make sure to connect with some of the people in that group, I guess.
Yeah, I'll put you in touch with them. But and I also wanted to say, like I said, I know nothing about this actually, but I admire you for trying to give a talk where you explain as much of it as you can to people who aren't experts, because I've been to several quantum talks, and a little bit more connects each time, but I think this is a really good one. So thank you for coming.
Thank you.